Good afternoon, everyone, and welcome to my session on co-scheduling CPUs, GPUs, and TPUs with some architectural trade-offs that we will discuss for the HPC, high-performance computing performance, energy, and cost. My name is Phani Pendurthi. I work at Mastercard, primarily on distributed systems, event-driven platforms, and AI/ML engineering at scale. So this is kind of brief agenda that I would like to talk through and the slides that I have. Over the next 20 minutes, we're going to talk about one of the most important and honestly underappreciated problems in high-performance computing. How do you actually schedule work across CPUs, GPUs, TPUs at the same time in heterogeneous HPC environments? Do we ever try? I know there is some research happening, specifically between CPU and GPUs, which is at TU Munich. There is a paper that's out there, and they tried between CPU, TPU, but my talk is more extending that to all three chips that are available out there, and the fact that the AI workloads that are actually increasing today, which is at log scale, it's doubling about every 3.4 months, and it's keep climbing, which is exponential and at a log scale. So there is no way that we can actually meet the demands and a single GPU cluster or a chip that can actually handle this. And most importantly, the HPC performance, as much as it is important, the power, energy, and cost also as important as, because it has to be economically stable. So as I mentioned, the single architecture systems can't scale affordably to meet this demand. The CPUs are brilliant at control flow or branching logic, as we have used many years, almost 3 decades, but they simply don't have parallel throughput for tensor-heavy AI workloads, and thus the GPUs have come up. GPUs are designed for high parallel workloads, but if the task includes a lot of conditional logic or branching logic, such as graph traversal or mixture of expert models or irregular sparse operations, GPU become underutilized. That's primarily because the threads diverge, warps serialize, and you are burning power on idle cores. So those irregular tasks really belong on the CPU. And so co-scheduling is what makes that routing possible. Similarly, TPUs are incredibly fast, but inflexible. They thrive on uniform, fixed-shape tensor operations, but struggle the moment that pattern breaks. Variable sequence lengths require padding or recompilation, which primarily works on its architecture that is systolic arrays, that is a grid of compute units. Any workload that deviates from dense operations, like matrix multiplications, it either gets rewritten to fit or it loses efficiency at fast. So that's precisely where the co-scheduling comes in. You don't rewrite the workload, you route it. The dense matrix operations go to the TPU. The variable length sparse and control-heavy parts go to the CPU or GPU in some cases. Each processor does what it was designed for. No rewriting, no padding based, or no efficiency loss. Again, power consumption is now a first-order concern in almost all high-performance computing systems, from embedded devices to supercomputers. It's not just about maximizing performance anymore. Most modern systems must operate with strict power budgets, and every scheduling decision has energy implications. Any performance optimization, especially in HPC, must now be power-aware. Hence, the co-scheduling aspect come in picture, and the active research that's work out there. And as an independent researcher, I'm also trying to see the connection between all three power chips and efficiently distribute the workloads as they are designed for in different scheduling strategies. So as we move on, we can look at the scheduling strategies and how the data actually flows between these power chips or the clusters, but why heterogeneous computing is needed at all. It's obviously about the cost, but how do we achieve it? The hardware specialization is the core win. So when we map control-heavy tasks to CPUs, throughput workloads to GPUs, and dense matrix operations to TPUs, so you're talking about 10 to 100 times of efficiency in terms of performance. Again, beyond raw performance, it's also energy, power, and the cost. And it's not free. On the right, you see the real challenges, the coordination complexity. You are now synchronizing across 3 distinct execution models. Data movement costs between disjoint memory spaces if you are not careful. Dynamic load balancing under runtime conditions is really hard. And lack of unified programming languages like CUDA, which is for GPU, OpenMP, which is for CPU, or JAX for TPU, which lacks unified programming models. And it makes it harder to switch the workloads between all these power chips. So to understand where to run what, if you take an example of the specification on the hardware, CPU runs up to 128 independent cores on DDR memory. GPUs bring 10,000 or more SIMT cores with high bandwidth memory with terabytes per second. As of today, the latest NVIDIA B200 GPU cluster model brings in about 8 terabytes per second with the high bandwidth, high memory bandwidth. But there are drawbacks to it if we make up that cluster and don't distribute the workloads efficiently. Similarly, on the TPUs, they bring the systolic arrays which hit hundreds to 900 tera operations per second, and with a massive on-chip SRAM. So these are all completely different profiles, and the execution model is what that matters. Again, the CPU's architecture is mainly on multiple instruction and multiple data, which is MIMD. So think of it as a small team of skilled generalists, each doing their own thing. This is highly flexible, ideal for control flow, branching logic, or irregular memory patterns like graph traversal or decision-making logic. Out-of-order execution and sophisticated branch means CPUs are really smart about hiding the latency. GPUs, in contrast, brings in SIMT model, single instruction, multiple threads. Think of a GPU like a massive army of identical soldiers. This is extremely efficient when the workload is regular and highly parallel, like image processing or matrix multiplies. But if different threads start branching, say some need to perform one action and another different action, then GPUs has to serialize the operation, which is where the divergence comes in, and that leads to stalls and underutilization. So the core insight is GPUs love uniformity. So how do we bring in the balance? So the GPUs has to be paired with CPUs, not out of the architectural necessity, but because running sequential operations like I/O or pre-processing on a $30,000 compute card is simply inefficient. On the other side, TPUs operate on systolic arrays, so which is a data flow architecture where the data pulses rhythmically through grid of compute units. This structure is extremely efficient for the dense matrix multiplications, like those used in deep learning. This is what that makes them better energy efficiency per flop on dense workloads. And it's why the TPUs, very recently, that most of the Gemini models are run on the large cluster of TPUs than the GPUs, and also because they are energy efficient in terms of making it cheaper and cooler to run at scale. So again, as an analogy, think of systolic models are like the factory assembly line. Data moves in one direction, and computation happens in parallel. Like dynamic control, and the data moves in one direction, computation happens in parallel, and the results flow out. But the trade-off is inflexibility. It only works well when the computation fits this fixed pattern. If there is a branching logic, any sequential operations, it falls off. The TPUs must become less effective. So this is why TPUs must be paired with CPUs, and the CPU handles all the regular logic that the systolic arrays can't. So these execution models aren't interchangeable at all. So they have very different strengths. Mismatching workloads to architectures don't just cost performance, but energy and money. Let's now look at the memory architecture as well between all these power chips. So memory is often the hidden bottleneck. And the latency chart on the right side tells you why. The remote PCIe, which is roughly 1,000 times slower than L1 cache. That gap drives almost every optimization decisions in the heterogeneous systems. The three different memory profiles comparing between CPUs, TPUs, and GPUs. CPUs run on the standard DDR memory with large multi-level caches. And they're smart about prefetching, pre-processing, executing branching logic. GPUs are built for bandwidth. As I mentioned earlier, the NVIDIA B200 brings in 8 terabytes per second. But the drawback of it is it only pays off if the workload feeds into the high bandwidth memory and it fills into the aligned blocks. Scattered or strided access pattern completely underutilizes the GPU clusters. TPUs pair the high bandwidth memory with massive on-chip SRAM. You stage weights onto SRAM once and reuse them for thousands of parallel matrix operations, and without having to go back to HBM. So that's the real difference. Again, TPUs can excel when the data pattern fits to the TPU architecture. Anywhere there is branching logic or sequential operation, it falls off. It makes it very inefficient. So keep in mind, moving data across GPU, CPU, GPU, or TPU, GPU, CPU, CPU boundaries is expensive regardless of the interconnect. If your workload bounces back and forth between the devices, you are losing efficiency again on every crossing. So it's really important to understand the architecture before we make a decision of what kind of scheduling strategies to move the data between all these systems to, at the same time, to achieve the highest performance and energy and efficiency on the cost. So just on the programming side and the drawback that I had mentioned, it's not easy to bring in all these core scheduling together. Especially on the top left, you see the OpenMP for CPUs, the parallel loops with Pragma directives, which are low barrier to entry, but it doesn't help to do the same programming on GPUs, which is CUDA, very specific to GPU programming. And on the other side, TPUs, which is JAX for TPUs. It compiles on Python and NumPy style code to XLA. So bottom right, Skycle, that's an attempt on the open source, the cross-platform, single source code targeting CPU, GPU, and other accelerators, bringing gate portability story. But there are some trade-offs with fine-grained control that you would lose with the Skycle. There is very active work going on with respect to Skycle, but it's still, we are far away from having any unified programming language to execute any workloads and do co-scheduling between any of these power chips. So how can we do this? So besides the unified programming languages, so let's now talk about some scheduling strategies and based upon some research that has happened in 2024. So on the top left, static scheduling. It is the distribution decided upfront from offline profiling, zero overhead and deterministic. So this is ideal for predictable training loops. It's brittle though. When device throttles, nothing compensates. The one in the middle, which is semi-static, It adjusts partition boundaries every n iterations via feedback loop. It can handle thermal throttling and phase changes, which is a sweet spot for many of the high-performance systems today. So the last one, which is the dynamic scheduling. This is based upon the very famous work stealing algorithm and also the autonomous machine learning based algorithm that can be possible to apply the dynamic scheduling. So the ideal devices steal away the work from the busy ones for maximum utilization. But look at the overhead bar. It's very high. And that's a real warning. So we only want to try out the dynamic scheduling when your load is genuinely unpredictable. So the big question is, how can the dynamic scheduling is possible? How does an ideal device decide what to steal? It's not random. The scheduler scores each task per device. Does the speed up outweigh the transfer cost? If yes, steal it. If not, wait. And co-scheduling only kicks in running together actually beats running alone. The moment contention is the gain, it falls back to sequential. As mentioned at the top of this slide, there is a reference to the research that has happened on 2024 at TU Munich. They have used a neural network to predict the co-scheduling between the CPU and GPU, applying the machine learning algorithm to find the optimal job pairings, and achieved 67% throughput improvement on real hardware. I will not go through all the power equations here, but just to note that these power models are very crucial and what makes power-aware scheduling quantifiable. Without them, the energy operation is just a guesswork. Let's now talk about the total cost of ownership. As we all know, with all the expensive hardware models that are coming out there, beginning with CPU, GPU, or TPUs, the 4 references come in picture when it comes to operating efficiency. The capital expense is very high at the beginning. If we run our own data centers, the OpEx operating expense, which is the power and cooling for dense GPUs and TPU clusters, and the management overhead, and obviously the last one is opportunity cost. If an ideal GPU is waiting in a job, still burn the power and tie up capital. And essentially the smart scheduling directly attacks all of the above 4, especially if you run your own data centers. And at the top right, we can compare those into the cloud-based deployments, but at the same time, we always get logged into the vendor as well as the total cost of ownership over 3 years is going to be high, although the initial capex is very low. So I just ran some simulations, although I'm not able to show it here, but just taking some references on the previous large language models, which is a GPT-3 that's trained on 175 billion parameters, just looking at what they have run, which is huge GPU clusters that can be broken down into 3 different possible distinct workloads by using CPU, GPU, and TPU, and efficiently train the same model and with very less cost and high energy efficiency. So if you just take a look at the CPU, as mentioned earlier, the data pre-processing, optimizer state, the checkpointing can all happen in the CPU. As far as GPU is concerned, the attentions, the layer normalizations, activations can happen in parallel, which is all meant for GPUs. The TPU handles the dense matrix multiplication and backbone computations, which is a systolic-array's sweet spot. This is what I call it as the principle in action. If you can take this as a reference point for the future advancements in the research between, as far as the co-scheduling is concerned, between CPU, GPU, or TPU, GPU, or across all three, it's going to be game winning rather than investing a lot of cost into the enormous GPU data centers or TPUs even. So just similarly, there is another case study as well that I have run through, which is real-time object detection pipeline. So, and just for, so which is a use case that is running on the edge devices. Again, run the appropriate workloads to each of these power chip models to achieve high energy efficiency, cost, and performance. So finally, so all these workloads are very distinct. The important aspect here is to choose the right workload for the right architecture and maintain the co-scheduling. So begin with static scheduling and move to semi-static. Don't just go with the dynamic scheduling just because it is sophisticated, as anyway the aspects around the dynamic co-scheduling is still evolving, and a lot of research is happening there. I would like to connect on this if you have more questions, or happy to partner with if anybody interested in the research work of this co-scheduling between all three power chips. Thank you all.
Thank you so much. We have time for a couple of questions.
You talked about 2 case studies. Is it based on the paper? Or?
It's not. It is just my independent research on the, so as you see, the case study was back to the GPT-3 class model, which was, I guess, 2024. So just looking at what GPT-3 was trained on for the 175 billion parameters is all on the GPU, large, enormous GPU clusters. So my idea is that we fit the right workloads to the right architectures, and so bringing in the high energy efficiency and performance as well as the cost.
So this is static scheduling between the two?
It is semi-static scheduling. So just to make sure, this is just a directional reference for the future research that can happen for the co-scheduling that can, especially if we target towards the dynamics co-scheduling with machine learning and prediction, automatic prediction that can happen.
Is Mastercard as a company using TPUs and GPUs
and
no. CPUs right now?
GPUs to some extent, yes. CPUs, obviously, yes.
So did you say TPUs or GPUs?
No TPUs, but CPUs and GPUs.
Okay.
To learn these small machine learning models, and to some extent the GPUs for heavy machine learning models.
Any other last question? Not? Yes.
Yep.
Tell me about the assumptions that you're making with respect to resource availability. So it kind of sounds like you have these TPUs hanging out, GPUs hanging out, CPUs hanging out. In a realistic scenario, it likely is the case that you can't just get access to GPUs and TPUs when you want them. And so how do you account for sort of the temporal cost of waiting when you think about this co-scheduling?
Sorry, I missed the last second. There is some noise in the background. What is the last part of it?
Yeah, so how do you take into account the temporal cost of waiting? So let's say that you want them to work together as a team, but actually you need to wait hours or some, to actually get access to the resources. Does that change your thinking at all?
So you are talking about how do we ensure that the resources are idle
Well,
Or-
you can't really ensure that you get, let's say we're using clouds, right? So we don't have on-premises clusters just sitting and waiting for us to use them. We have to ask for them from an on-demand model. And so when you're doing that and you say, oh, it's time for the TPU to work with the GPU, but you can't get any TPUs because there's resource contention. So how does that change your thinking in this problem space?
So you're talking about the resource contention when there is a need for the GPU and GPU resources are unavailable.
That's correct.
Well, we got to scale the GPU cluster, I would think, especially when that's the workload that we target programmatically to run on GPU and the GPU resources are unavailable, then we got to size the cluster for what we need to run that workload, right?
And then if you can't get access to GPUs either, you have to figure out how to run your work on CPUs?
No, again, so the right workload fitting to the right architecture is still important. Otherwise, we lose that efficiency, even if it is with performance. We can't run the dense workloads or any matrix multiplication that GPU can run or TPU can run on the CPUs.
Right. I think the main kind of thing I wanted you to think about is the fact that you can't always get access to all of these better resources that you need.
Absolutely.
Yeah, but thank you for the talk.
Thank you.
Thank you. Okay, with that, the session is over and we have a break right now. Thank you.